doing a presentation on DYODE, do your own diode, DIY, and low cost diode for ICS, for industrial control systems. Without further ado.
Okay, am I good to go? Do you hear me well? Okay, so. Okay, is it better?
A little bit.
Okay, I'm just trying to speak louder. Okay, so thanks for attending this talk. I'm going to talk about a project that we created with one of my colleagues, Ari Kokos. Unfortunately, he's not here today. This project is called DIODE, which stands for Do Your Own Diode. The idea is to create a low-cost, do-it-yourself data diode aimed at industrial control systems. The thing is, it can be used for other things, but mainly it was designed for industrial control systems. So before I start, just a few words about myself. My name is Arnaud Soulier. I work as a senior consultant at Wavestone, which is a consulting company. I mostly do penetration testing. I've been doing that for about 6 years now. And I started working on ICS security, I would say 4 years ago, like everyone else after Stuxnet. I also do a bit of research, hence this project and this talk today. My interests in security are Windows Active Directory security. I gave a talk about that a few years back in France. And also SCADA security workshops. So I'm doing, let's say, a 101 session to introduce SCADA security to IT people. I will do that tomorrow morning here at the B-Sides and also on Thursday morning at DEF CON. And I also like wine tasting and motorbike riding, which is not in the scope for today. Okay, so we're going to start with what I would call an ICS crash course. The idea is just to give you the required knowledge to understand what is an ICS. So let's start. Where can we find ICS? So it stands for Industrial Control Systems. So these are the, let's say, the systems that help people create stuff in the manufacturing plants, in power plants, in building automation, water treatment, also in the pharmaceutical industry. For example, let's say you want to create pharmaceutical drugs, then from the biological steps to, let's say, putting the specific liquid into the vials, to the packaging, everything is controlled by specific systems that you call industrial control systems. You can also find these in what you can call critical infrastructures, which means, let's say, electrical plants, dams, in the nuclear sector, things that can really go bad if you cannot secure it correctly. Okay, let's continue. This is a very, very simplified network diagram, just to introduce the components that we can find in an ICS. So let's start from the right. You will see here you have specific devices. We will call that sensors and actuators. A sensor will simply give you, let's say, a feedback on the physical world. For example, temperature, pressure. Those are the things you can use as a sensor. And you will have just the opposite, the actuators that will perform an action in the physical world. So most of the things, they are controlled, let's say, by electricity. For example, if you have a motor and you apply a specific voltage, it will start spinning. And so to control those devices, we use what is called PLCs. That stands for Programmable Logic Controller. Those are like, I would say, tiny computers with real-time operating systems. And their specificity is to have electrical inputs and outputs. That means, for example, the PLC can be used to, if I take really the most simple example, you can wire, let's say, a switch to the inputs of the PLC and wire a light bulb to its output, and then you can program the PLC to switch the light on when you flip the switch. So of course, that's a silly example because you can do the same without the PLC. But the advantage of using the PLC is that if tomorrow let's say your industrial process changes, you just have to reprogram the PLC. You do not have to rewire everything. So that's why we use PLCs. Sometimes you may also encounter the term RTUs, which stands for Remote Terminal Units. Basically, it's a standalone PLC. So here we are with electrical connection. Here we already have network connection, and to program the PLCs and to control them, we have what we call the supervision network or the SCADA network. Actually, it's not so precise to say SCADA, but it's the most used term nowadays. On this part of the network, you will have, let's say, basically Windows operating system, standard workstation, servers, and the people working in the plants and factory, they will be in front of Windows workstations. They will check that everything works fine in the process and click on some buttons to perform actions in the physical world. Then this supervision network, it's always somehow connected to the corporate network, which is somehow connected to the internet, because you have to read mail and then go on YouTube. Okay, so that's basically a simple network diagram for ICS. And I suggest we continue by introducing the security level nowadays of ICS. So here again, I'm oversimplifying just for the sake of introduction. The problem we have in ICS security, the PLC, when they talk to each other or when they exchange information with the SCADA network, they use specific protocols. We can say Modbus, Profinet, S7, and they all share the same thing. It's the lack of security. If you're able to, let's say, perform man-in-the-middle on those protocols, you will be able to, let's say, understand what's going on because it's not encrypted. You will be also able to, let's say, replay some commands to perform actions. But the worst thing is you actually do not need to be in a man-in-the-middle position because you just simply can send unauthenticated commands. So that means that if you're on the same network than a PLC, you can simply send commands to read or set some values. For some PLCs, it's worse than for others. For example, on Schneider PLCs, there is an undocumented function they use in the Modbus protocol, the function code 90. And that's what you use to program the PLC. And since it relies on Modbus, which is unauthenticated, that means that if you can reach, from a network point of view, the PLC, then you are able to download the program that's running, modify it, and then re-upload it. So if you translate that to the IT world, it would be the same as just because you browse a website, you can change the code on the server side. So that's pretty bad. And you have to assume that as soon as you have a network connection to a PLC, you can own it. That's the, let's say, I would say the state of security that I encounter when I perform penetration test. Second thing, network exposure. You may think that those PLC, they are in specific plants, factories, and so they must not be reached from the outside. That's not really the case. You have plenty of PLC directly exposed to the internet. That's a showdown search I did maybe last week. So you can see that there are 3 Modbus devices in Las Vegas. I don't know where. I did not perform any kind of test. That's not my point. My point is to say you have devices exposed to the internet, and as soon as you have network access, you can fully compromise the device. So that's really bad. Okay, so what can we do? Of course, we want to perform some kind of network segmentation. So we have technical solution, we have firewall, we have DMZs. That's really great, but that's not the challenge. The problem is that, as would Dr. Malcolm say in Jurassic Park, life finds a way, and it's the same for data. If you try to isolate the ICS network, people will use USB keys, they will use Wi-Fi access points, they will use tethering, they will tether their internet connection with the phone. So that's not the challenge. The real challenge is to be able to perform network segmentation while allowing secure data exchange. 2 simple use cases. The first one, sometimes people want to perform security updates on their ICS. Not so frequent, but it happens. So there's a legitimate need to be able to transfer the updates from the corporate network or from the internet to the ICS. And the other use case is the need to, let's say, export some production data from the ICS to the corporate network to be able to, let's say, design dashboards for the COMEX. A solution to that is the use of data diodes. Why? Data diodes, you can also call that one-way gateways. They use light as the transport medium, and you can use some of the properties of the specific of the optical components to have a very secure connection. Why? Because when you use, let's say, light as the medium, you will have some, on one side, a light-emitting diode that will create a light that's going to go through the optical cable. And this light-emitting diode has what we call a PN junction. So that's, let's say, for those of us that did some electronics, that means that electrons, they can only flow from one pole to the other and not the other way around. So the security principle is backed by physics. So in theory, it's really, really secure. That's the main point of the data diode. It's allowing communication to go only one way with a really high security level. Okay, so why did we start this project? It's mainly because of the feedback we had during our assessment. Ari, my colleague, did a lot of consulting for ICS security. I did a lot of pen testing, and we realized that in most of the cases, there were data exchange needs, but they were not done properly, mainly poorly configured firewall and stuff like that. Also, commercial data diode, I did not invent the concept. It's used for decades in, let's say, in the defense area, for example. So it exists, but it's quite expensive. So there's a trade-off between the cost and the security. Most of the time, a data diode will cost between 5,000 and maybe to 50 or 100,000, depending on your need. So of course, if your client needs to have, let's say, a synchronization between the ICS and here it's SAP instance, maybe it's willing to pay 50K for that. But we encounter a lot of situations where there was a need. It's not really, you do not have a high availability need, you do not need a lot of bandwidth, and so the client will not pay 50Ks just for this small need. That's the main problem. I have two examples here. The first one is about predictive maintenance. That's a concept in which, let's say, often it's a third party is able to, let's say, to predict what kind of PCs in your ICS will wear, and so automatically order new ones. So that's kind of magical. And to do that, what you need is, in this specific case, was to send a 100 kilobyte file every 6 hours. So you see that the size of the file is not really high. If you do not send the file, the process continues to work. That's not a problem. You can send the file the day after. Second example that I encountered during an audit in the pharmaceutical industry, it was refrigeration units. It was, let's say, maintained by a third party that needed to have real-time access to the PLC data in order to improve the efficiency of the system. So that was in the contract. So there again, if, let's say, the connection to the third party fails, the system will continue to refrigerate. That's not a problem. So you have specific needs that do not justify the investment of several dozen of thousands of dollars. So in those two examples, what did our clients do? Mostly they just connected an uncontrolled third party directly to their ICS. And as mentioned before, that's not a good idea because if you have network connection, you can just mess everything up. Okay, so our project is not completely new. It's based on existing work from Philippe Lagadec, French guy, Austin Scott, or Robert Gabriel. The idea is to use standard commercial off-the-shelf hardware and open source code to produce a data diode with a target cost of about $200 per unit. What did we want to do that? To have a working proof of concept. We wanted to try to create, let's say, an easy-to-use solution, easy to deploy, share the results. Also, just note, we do not have any commercial intent with this project. It was mostly to show that it's possible to create your own device. But if someone is interested in creating or selling those kind of cheap device, feel free to do so. We would be happy, and we do not want any royalties. We do not want to sell boxes. We do consulting. Okay, so for the hardware, actually you have the hardware here. What we do for this data diode is we use copper optical converters to have an optical connection between the ICS and the corporate network. So how does it work? First thing, it's not possible just to use a one-way connection. It's not that simple, because most of the protocols that we use every day, file sharing using Samba or Modbus relies on TCP. So if you want to do TCP, you have to do the three-way handshake. You send SYN, you receive SYNAC, you send ACK. That's not possible, because if you have a one-way channel, you're going to send your SYN and never receive the SYN ACK. So that's why we have to use two computers, here and here. We use Raspberry Pis because that's kind of inexpensive. And they will be in charge of performing some kind of network protocol translation from TCP to UDP to allow communication to flow through the diode. So how does it work? So here you have an Ethernet cable from the ICS to the first Raspberry Pi, which is connected to this box. It's the copper optical converter, which then has two ports, one for data emission and the other for data reception. So the idea here is to only have one cable that goes from the transmission port on the first one to the reception port on the second one. Since there is no cable the other way around, data cannot go the other way around. So that's kind of simple, but in real life it doesn't work. Why? Because the first box will not accept to send data if something is not plugged into the reception port. So that's why we use a third converter just to simulate an active link. But this box is connected to nothing. Then the data will be converted to the copper Ethernet to the second Raspberry Pi that will be connected to the corporate network. That's the basic idea. Here you have a picture of the inside of the box. So as you can see, it's not so messy actually. You have all the electrical stuff on the left. You have the two Raspberry Pis. That's range. It means input and output on the little stickers. Here you have here you have two optical converters stacked one on each other. Then the third one, as you can see, there's only one cable that goes from here to here. So that's the communication channel, and there's no channel going from transmission to reception here. Okay, so just a few words about the real cost of the product. So we aimed at $200. Clearly we failed. Actually it's more like $400 if we convert euros to dollars. Why? Mostly because we wanted to have screens. As you can see, you have two small LCD screens. It's not really useful, so that was kind of a mistake. It's really not necessary. And also what was the most expensive part was actually the 19-inch aluminum rack. But since everyone wants blinking boxes, we thought it's a good idea to put it into a rack if we want to be taken seriously. Okay, so I'm not going to wait until the end of the talk to perform the demonstration. Of course, I have a video backup. I'm seriously hoping not to use it. Oh, wait, we got one more slide. So here, what is the setup? Just consider that this PC will emulate the ICS network, and a VM on my PC will emulate the corporate network. And between the two, we have the data diode that is just here. Okay, so the first thing I want to show you is how to transfer a file. That's the first feature that we did, is the ability to transfer a file. Okay. So I'm going to try to do something. Is to film this screen so you can see what's actually going on. let's skip the video part. So the idea is quite simple. The idea is that you copy a file on the network share on the first Raspberry Pi, and the file ends up on another share on the second Raspberry Pi. So for example, here, so on the corporate network, there's no file at the moment. Okay. Okay. I was strongly hoping not to use the video, but okay. Not working so well. So the idea was simply on this computer to copy a file, and a few seconds later it should appear on my computer. But I can't seem to open the file share. Okay, yes. Okay, so here is the file I copied, just the logo from my company. I will do the same with a slightly more bigger file, which is 1 megabyte. Okay, so let's try again. Okay, so the file is copied on this side, and in a few seconds or in 1 minute it should appear here. I will talk about that later, but the speed is actually not so great, which is not too bad because, as mentioned, we do not target high availability or high bandwidth needs. Okay, wait a sec, it should appear in a few minutes. So also what's interesting is that since there is no bidirectional communication, you can actually use the same IP address on the two Raspberry Pis, which means that you do not have to configure anything on the ICS side or on the corporate side. Okay, so that's the Java file I was sending. So as you can see, it's a 1 megabyte file, and it took about 30 seconds, so really kind of slow, but it works. The second demonstration I'd like to do, you have it here. I'm going to make the screen slightly bigger. Okay, so that's a Modbus client. So let's say I want to transmit Modbus data using the diode. Here on this PC I have the simulator, and I'm going to change the values that you can see. So I'm going to change the 1 to a 0, and then put the following one to 1. Yeah, so as you can see, the delay is maybe about 500 milliseconds or 1 second. Works quite well. So those were Modbus coils. Of course, we can do the same with Modbus registers. So I'm just going to put 1, 2, 3. Yeah, and like as you can see, it's modified. Okay, and the last feature, which is kind of interesting, is the screen sharing. So let's say you're on your ICS, you need the help of your vendor to perform some debugging operation, but you do not want to expose RDP directly to the internet and let your provider do whatever it wants to do. So with this solution, we offer a one-way screen sharing. That means using a simple web browser, the third party would be able to see what's on the screen, and being on a conf call with one of your employees, it can help you click on the right icons and perform the action, but you keep doing the action. It's not the provider that does the action, so that's, I think, a better security mechanism. So here also, as you will be able to see, there's about a 1 second delay if I move the... it's going from this PC to this one. The screen sharing goes from the ICS network to the corporate network, or to the internet, let's say. I'm going to explain the whole workflow in the following slides. And also, as you can see, yes, just open a video. It's really not suited for video. You have 1 or 2 frames per second, so it's really not working that well. However, the resolution is high enough to let you really see what's written, so I think that for remote maintenance, it works kind of well. Okay, let's switch back to the slides. Okay, so I talked about the hardware. Now I'm going to talk about the software. We wanted to have a solution that's working quite quickly. We didn't want to invest 6 months in development. So what we did is reuse something that already existed. It's called UDPcast. It's an open source application. And it has a feature to send data through a one-way channel. It was mainly designed for satellite communication, where the downlink is quite cheap, but the uplink is expensive. So using this application, we were able to, let's say, have the core of our product, and we produce some Python code to use that application to do file transfer, Modbus transfer, and screen sharing. We also have a quite easy to understand configuration file, and it's only about 500 single lines of code. So what happens when we transfer a file? So on the ICS network, you're on a PC, you copy a file to a share. Then what the Raspberry Pi will do is calculate a checksum of the file, put the checksum and the file name into what we call a manifest file that will be sent to the second Raspberry Pi. And then you send the actual file. You receive the file, you calculate the checksum. If the checksum is the same as in the manifest file, that means the data transfer went well. And so the file is copied to a network share, and you can access it from the corporate network. For Modbus, how does it work? You actually have a Modbus client on the first Raspberry Pi. Every second, it's going to request some values from the PLC, put those values into a JSON object that's going to be serialized and send using sockets to the second Raspberry Pi. It's going to be deserialized. And on the second Raspberry Pi, we have a Modbus server that we instantiate, and the values of the Modbus server will be updated with the values sent by the data diode. So that means that on my PC, I was not directly addressing the PLC. I was addressing the Raspberry Pi inside the diode. Lastly, the screen sharing workflow. So on the PC of which I want to share the screen, I have a PowerShell script. It's really easy, it's maybe 10 lines of code, that will take a screenshot every 500 milliseconds and save that to a network share on the first Raspberry Pi. Then the Raspberry Pi will use sockets to send the picture to the second Raspberry Pi, on which we instantiate a web server that will serve an MJPEG file. That's technology that's mostly used for webcams. So that means the client does a GET request to MJPEG file, and then the server keeps sending the new pictures, and it looks like a video, where it's just a series of pictures. Yeah. Does that answer the question on how it works? We may now take a look at the configuration file. So as you can see, it's quite easy. You have, let's say, the useless stuff like the name of the configuration, the version, and the date. Then we have some properties about the Raspberry Pi's, IP and MAC address, because then again, since the data only flows one way, you have to use static RRP. It wasn't, first time we tried to make it work, it didn't work at all. It was because there was no response to the RRP broadcast. And then you just define all the modules that you want to use. So at the moment, we have 3 types of module: file transfer, it's called folder. So you just have to choose a port number, which must be unique, and the file path for the input and the output. If you want to add a Modbus PLC, you just type Modbus. Then you define the IP address of the PLC. Then you define on which port on the second Raspberry Pi will be instantiated the server, and then you define the values that you want to copy, because we cannot copy all the values. It would take too much time, so you will just define what kind of values we want to copy. And lastly, the screen share looks like the folder. It's actually kind of the same directive in the configuration file. So as you can see, it's quite simple to use and to configure. And the configuration file is the same on the first and second Raspberry Pi. So that's easier to perform. Okay, now this is an interesting question that I received one morning from one of my colleagues. Came into the office and said, what's all the fuss about this diode? It seems overly complicated. I can just use an Ethernet cable and cut two of the strings inside, for example, the two reception strings, and then I have a one-way communication medium. That's easier. This is kind of true. However, as mentioned, the main problem is that all the protocols, most of the protocols use TCP, so you still need to have the Raspberry Pis, for example, to perform the protocol translation. And then, some may sound NSA-like attacks, but in theory, if you use an Ethernet cable, even if it's cut, and you use half duplex mode on each side of the Raspberry Pis, you may perform port up and port down actions, and that may be used as a side channel attack. So actually using light as the medium is the only thing that ensures that there is no back communication. But actually you can build a working solution secure enough without the optical copper converter. That's one option. Okay, then what are the limits of this project? So at the moment it's really, really slow, maybe 1 to 2 megabytes per second tops. And also there was a high latency caused by the flat file transfer, because as mentioned at the beginning, we use UDP-cast. So from the Python code, you use an external binary which displays some things on the console before really launching. So you have at least a 2-second delays, which is not good for Modbus and screen sharing. So we replace that. We only keep UDP-cast for the file transfer, and we use a very basic, naive implementation using Python UDP sockets to send the Modbus data and the screen sharing. Other problem at the moment, let's say this box is not production ready. It's working, but it needs to add more, let's say, error catching. If something it may be buggy a bit, and also the components are not really meant to be used in, let's say, harsh environments like we sometimes encounter in ICS. So it's not dust proof and stuff like that. But it's working quite well at the moment. Okay, so maybe we can take a step back. So I explained what is an ICS, why we need data diodes, how my data diode works. Then let's think, is it magical? So the whole idea of doing a data diode was to have data flowing only one way. But as I mentioned at the beginning, most of the time you need to exchange data in 2 ways. Updates, antivirus signatures need to flow from the corporate network to the ICS, and the production report needs to flow from the ICS to the corporate network. So in the reality, in the real world, you may end up using 2 different data diodes, one from one side, one on the other side. So yes, you will still have a high level of security, but that goes a bit against the principle of having one-way communication. In reality, it's not that easy to have one-way communication, and you may imagine that a malware may be able, it's going to be very complicated, but it may be possible that you can have a communication channel with the control command that goes through this diode on this side and through this diode on the other side. So I'm not saying that diodes are not good. I'm just saying it's not magical, and it's not as simple as putting this box to secure everything. Next, still on the same topic, what exactly guarantees the diode? Only one thing, data is flowing one way. So that means that if you want to have a secure solution, you still need to perform all the kinds of logical security and hardening that you perform on your devices. If the output Raspberry Pi is not secure enough, you have default credential, SSH exposed, you may be hacked. That means someone could perform a denial of service, or could also, let's say, on the fly modify the Modbus values. So it's not enough to have a one-way communication. You still need to perform standard security. Okay, the roadmap for the project. So the next step that we want to take is make it more reliable by using a heartbeat feature. What we call heartbeat feature is the, let's say, ability to send a defined file maybe every half an hour. And so if we do not receive the file on the second Raspberry Pi, we raise an alert, or we send an alert to the syslog to say, hey, something is wrong. A bit of security hardening. We aimed at the beginning at providing, let's say, complete and ready-to-use images for Raspberry Pis, but that takes time. Possible improvements for which we may need your help. Adding more protocols. At the moment, you have file transfer, Modbus, and screen sharing. We'd like to have S7 protocol, the one used by the Siemens PLC. It's not too hard to do, I think, but because there are open source libraries that will help us. It could also be interesting to have a syslog feature, SMTP feature, maybe integrate some kind of integrity check on the data. Having cryptographic signature on transfer file would also be interesting for high security environments. I think it's not going to be that hard to implement. But really the next big project is this one, is the ability to use infrared as the communication medium, because that would allow us to, let's say, remove the 3 copper optical converters and just have let's say, a light-emitting diode on one of the Raspberry and a light receptor on the other side. So of course that's going to be really, really slow. But if you just need to let's say, to synchronize 20 Modbus values, that's enough. So with this solution, we aimed at a solution about $50 maybe if we use a Raspberry Pi zeros and just infrared devices. Okay, I think was really, really fast. So the code is on GitHub. The code on GitHub is working. However, it's not the latest versions. I actually did some modification and improvement just before leaving, and I did not do a git push. So it's on my work computer that's in France. But so maybe if you want to try the project, wait just 1 week or 2. So I have time to come back and push the new version. But the version that's on GitHub is working. It's just not as reliable as the latest one. And so, again, if you want to help with this project, if you find it interesting, just do whatever the hell you want with it. We do not want anything. We were hoping to help and to show that if something is missing from a security point of view, being in software or in hardware, maybe there's a solution to do this yourself. Okay, so do you have any question?
Wonderful. I'm going to open the floor up for some questions, but I'm going to cover something I missed. I'm going to do some name dropping our sponsors. It wouldn't be possible if it weren't for people like Versprite, Protivity, Tenable, Amazon, and Source of Knowledge. Thank you.
Yeah, I had a question. You were sending info from one Raspberry Pi to 2 Raspberry Pis, one of which would respond. How did you split the light between the two so it went both ways instead of just one?
Okay, you were talking about this slide maybe?
Oh yeah, you did it via Ethernet converters between the 2 top ones and Ethernet on the bottom. Or I didn't quite understand how you sent it both ways to 2 Raspberry Pis for transmit and
Okay.
one received.
Okay, so I'm going to do it again. So here you have your ICS devices. They talk using a standard copper Ethernet to the first Raspberry Pi. This one has a second network interface connected to the Ethernet copper port on this optical converter, which then has the transmission optical port connected to the optical reception port on this one. And so this one is only used because if you plug nothing on the reception port, the converter thinks that it's not working. So this is just to emulate a valid signal on the first converter to make it work. If you do not do that, it's not working.
I think it's a safety feature, actually. It's for when there's high-power lasers with fiber optics. They don't want transmission to happen without received connection. So there may be
Maybe.
some possible way to
I know that some of the models, this feature can be disabled in some of the optical converters. The one we found on Amazon, where we were not able to disable it, but someone, actually call for paper reviewer from another security conference gave us an interesting solution. He told us we can use an optical splitter to actually put the transmission signal back into the reception port. So that would actually, it could be cheaper, but the problem is those things, you do not find it on Amazon. You have to buy it from, let's say, China. And actually the shipping cost was so high for 1 or 2 splitters, then for us it was cheaper to stay with the converter. But let's say on a mass scale production, you will replace that with a splitter. That should work.
Hi. Did you consider using an opto-isolator chip, which you can get for about $2, and just run serial through it? I mean, you can run those up to 10 megabits, and it wouldn't cost very much. It's a standalone chip that has both the diode and the like an LED built right into it. I mean, they're used pretty commonly for isolating electrical circuits from each other. I'll check it out. I mean, it might be a way to really reduce the cost.
How do you call that again?
It's called an opto-isolator. They're used a lot of times to divide different parts of circuits from each other electrically.
Okay.
And I think that would probably be right up your alley for this particular project.
Okay, thanks.
Anybody have any other questions?
Have you considered using a proxy server on the Raspberry Pi that's connected to the corporate side, so you can proxy connections without breaking protocols there, and then you'd still have to do custom protocol fixes for communicating with the SCS side. But that's just an idea. I don't know if you considered that.
No, actually we thought the solution that we implemented, where you have a client on one side and a server on the other side, was maybe the most straightforward. So, but yes, a proxy would definitely work, but I think it would be more complicated from a software development perspective to code the specific proxy stuff than here, where I can just reuse existing libraries. For example, for the Modbus client and server, I'm just using existing Python code. So that's why it was so easy and hence so cheap to do that. Yeah.
Good job.
But that's not, I think, the most efficient way. I know that, but that's the cheapest way, I think. At least without using the optical isolator.
All right. Well, let's give another round of applause to our presenter, Arnaud from Waystone Security. Thank you.